igolgi has been providing encoding and transcoding solutions for broadcast, cable, IPTV, OTT, and VOD for almost 15 years. Those solutions power thousands of live and VOD channels every day. Presenting today are Jeff Cooper, CEO and co-founder, and Kumar Ramaswamy, president and co-founder. And I'll turn it over to Kumar.
Thank you, Rich. We are here today to talk about just-in-time transcoding scheme that we will be discussing in some detail about why is it different, what is just-in-time transcoding, and why is it relevant for the industry. So before I jump into just-in-time transcoding, I'm sure this topic is extremely familiar to all the audience here today, but we want to start out by talking a little bit about a little primer on adaptive bitrate transcoding itself, just to level set the whole topic. Most operators today, both on managed networks as well as OTT providers, distribute live and media content using ABR methods, adaptive bitrate methods. So what is ABR? Every media stream is chopped up into small segments, and various versions of these segments at various bit rates, and these are called profiles, are created. And based on the client's available bandwidth or other parameters, the client requests the server to serve up a profile on a segment by segment basis. And typically a segment may last 2 to 5 seconds. And so the client requests based on its available bandwidth, it may request the particular version of or a particular profile of the segment. And today in most networks, 4 or more profiles are created for every stream. They are cached, they are distributed throughout the infrastructure, and they are retrieved by end clients as needed. So this kind of brings us to the topic, why just-in-time transcoding? This whole topic of just-in-time transcoding for about a decade has been discussed and demonstrated by various vendors and things like that. But there are 2 primary reasons why just-in-time transcoding is very relevant. One is the long-tail phenomenon, namely content. About 80% of the content, about 20% of the content is watched about 80% of the time. So there's an extremely long tail of content that gets watched pretty infrequently. But remember, when we are creating ABR systems, we are creating all these profiles and storing them and distributing them throughout the infrastructure. And there is a second phenomenon that kind of comes into play, namely, if you remember, I said that there were various profiles created. It turns out that for most managed networks, less than 5% of the time, any of the lower profiles are requested, which means 95% of the time or more, people only request the top profile, which means you're creating a bunch of lower profiles that are created, managed, and distributed, but nobody ever requests them or watches them. This kind of rate of request of lower profiles is a little bit higher in unmanaged networks, but still fairly low. Most of the time, people are requesting the top profile. Now, that means that the entire system, right, that we have of ABR distribution today, there is a potential to save 50% of the storage throughout the infrastructure if one were to do just-in-time transcoding. The other aspect of this is, while just-in-time transcoding has been around for a while, recent evolutions in GPU and ASICs have made this extremely attractive. And it turns out that just because you're only creating the profiles as needed and on the fly, it also works out to be a fairly green solution. And we will be quantifying some examples later in this presentation about what that savings are. igolgi has created, we have spent the last few years developing the product called Blazar, and it is a just-in-time transcoding engine. It is built on a cluster of GPUs that serve as accelerants. And we use the key technology in this case is the use of very efficient scheduling engines that decides how to use the cluster of GPUs very efficiently for a whole host of functions, namely transcoding, scaling, deinterlacing, and a whole lot of other functionality that one uses in the video chain. And then we use the available infrastructure in a highly efficient way using a scheduling engine. And we can create segments, files, ABR ladders as needed. And this solution is available both on premises or in the cloud. So the key question is, why is Blazar even relevant? If one can go back and look at the kind of ABR systems, very early systems were built on the concept of a static ladder. Namely, the system would predefine a number of profiles that one would create. And this is called a static ladder. It was delivered in the form of a manifest to a client, and then the client would pick from the static ladder. Over time, people have realized that, hey, some content is much more easy to encode and things like that. So what they have done is they've come up with an adaptive content ladder, right? Adaptive ladder. So what that does is, based on the type of content, it creates a somewhat dynamic content ladder. But again, that's created in the form of a manifest and distributed to the client. Blazar can be viewed as an infinite ladder. The idea being that you have very fine-grained control of what the client optimally needs at any point in time. As an example, if the client were to request a particular bit rate, both with the static and the content-aware ladder, you may be far away from any available bit rate that's close to what is being requested. But with Blazar, you can create something extremely close to what is being requested. And hence, that results in fairly optimal distribution, both from a quality perspective, as well as from a bandwidth usage perspective. So we have several use cases for Blazar Just-In-Time Transcoder, and Jeff will go through these use cases. The big ones are cloud DVR, edge transcoding, as well as dynamic ad insertion. Jeff?
Thanks, Kumar. Good afternoon, everyone. Yeah, we'll go through a few use cases and then show a short demo of Blazar in action. The first one is the cloud DVR. Here on this diagram, we show a simplified view of a network with a cloud DVR in the system, an origin server distributing out to the edge caches and to the end devices. And what's in a traditional scenario in the cloud DVR, all the profiles for all the channels are stored on the DVR. Client requests, whatever profile it needs back to the origin server, and this gets distributed. And the edge caches try to optimize that network distribution. In a Blazar system, what we do is we just save the top profile in the DVR. So it's only created, so you only create that top profile. So the DVR is much smaller. And then when a device requests a profile other than the top one, the origin server routes it back to Blazar. And the Blazar transcoder is a very fast just-in-time transcoder, and under load can deliver those segments very quickly. We can scale it for different use cases, but in the DVR use case, it's usually less than 200 milliseconds, and we'll show that with a demonstration. So the big advantage here is the DVR storage is much smaller, and all the profiles aren't having to be distributed all through the network to the edge caches. So all that works more efficiently. Obviously, with private copy requirements in some networks or some channels require that, that's where this really has a big advantage. But in general, this is a much more optimum solution. The next one we're going to talk about is, again, a similar network architecture with an origin server delivering content to clients. And here we're talking about the use case where over time the codec used in the network is evolving. And what typically happens, if you're familiar with codec transitions through history, we've gone from MPEG-2, H.264, H.265, nowadays AV1, and many others sometimes. What happens is that the devices start to adapt newer codecs that are more efficient, but then in order to take advantage of that, the network operator has to both serve the legacy devices that don't support it and the new devices so you basically end up with both codecs encoded and stored and distributed through the network, which is very inefficient. So what Blazar allows you to do is to handle that transition much more smoother. Depending on which codec is the majority one, the one that is used less, you can set up Blazar to transition from one codec to the other. So for example, when a client that is available that has a newer codec comes along and you're still serving only the older codec, the new client can get routed to Blazar and transcoded to the new codec, which allows that transition to be more efficient. Typically, the new codec is more efficient. And then vice versa. When the legacy clients become the minority, then you can switch your network to the newer codec and take advantage of that. The next use case is digital ad insertion. So again, what Blazar can allow you to do is to more optimally serve a targeted ad in a short amount of time to a specific client. So we all know about targeted ads, and the ad insertion systems are becoming more and more smart. And when they make a decision that they want to put this ad for a certain person, often what happens is by the time that decision is made, the ad is delivered into the network and ready to go. You've missed the first advertising avail. So the first spot in the live stream has already gone by that you could have done it. What Blazar allows you to do is to hit that first avail, because it can go out through the cloud to any ad provider, download an ad, transcode it into all the profiles necessary in under 2 seconds typically, and insert it into the network. Typically ad avails are 4 seconds long. So from the beginning of an ad avail that just came along and you just know what ad to put in, you can still get that ad downloaded, transcoded, and delivered. And so your targeted ad, you get better yield for your ads. And finally, we won't talk about this very much, but Blazar is a scalable architected system, so we can do VOD transcoding very fast. So if you have a lot of content that is time sensitive and you need to transcode it really fast, we can scale Blazar to do any length content in just a couple minutes if that's what you need. And this is another use case we're seeing a lot of. So here in a minute, I'm going to switch to a short little demo of Blazar running in our lab. It's just a simple example where we have a source that represents a high definition signal, VOD signal that's stored on a server. And we'll have two players represented by two clients and two players in the demo that represent those. And one player will be requesting that source directly from the server, and the second player will request it at a different resolution, acting like it wants a lower profile, for example. And then Blazar goes to the source, downloads the higher profile, transcodes it very quickly, and delivers it to the player. And you'll notice that there's just a small lag between the two. So here's our demo. We have two players, and you can, in this demo, we have some preset resolutions, and you can randomly choose a bit rate. And when I hit this start button, then they both will make their requests at the same time. And you see that this on the left is the source that's coming directly off the hard drive. And on the right is going through Blazar. And the amount of delay here can be designed for any use case. Just moving on, as Kumar mentioned, we've done some analysis on the potential CapEx and CO2 reduction that is possible with Blazar, depending on the use case and many of the particulars in any network. But based on an actual 500 channel cable system that we've been a part of that had a 20-hour DVR service, we've shown that there was a 54% savings in CapEx, which is represented between the two lines here, the red line and the green line, and 73% carbon reduction or power reduction, which is the bar data. And all this details behind this are in a white paper on our website. You can see that this obviously grows with the number of subscribers. And I invite you to take a look at more details and contact us if you have some questions. Back to
Yeah, so I'm going to talk a little bit about the future of content distribution. One of the things that we have come to realize by looking at the ability to do just-in-time transcoding to scale is to kind of view how content distribution had started out with ABR as a convenience actually on the web. And now we have stuck with a system which is fairly inefficient from the viewpoint of distribution, because you're creating all these artificial bit rates and profiles that are never used in the infrastructure, but yet continue to be created and distributed. So our proposal is to describe a new form of content distribution, wherein the manifest that you have at the head end simply describes the limits of generation. Namely, it describes the top profile that is available and the rate at which the limits of bit rate, frame rate, resolution, and codec that can be supported at the head end. And the clients actually receive that manifest, and then they can make arbitrary profile requests on the fly. And why is this important? Because this then makes the overall delivery, the most efficient. So for example, if the client is able to realize that it can receive the top profile, it has enough bandwidth to do so, it will request it, and there is no processing that's going to happen at the head end. It just becomes a service delivery at that point. On the other hand, if it requests something, an arbitrary lower profile that needs to be generated, that can then hit a just-in-time transcoder, and the arbitrary profile can be delivered. So this actually can be done to scale, and we have done some analysis to show that this can be done, this kind of distribution paradigm can be done to scale. And this is optimal from the viewpoint of both the network utilization as well as the quality of experience for the client. This service, in this case, right, this is how we envision the future of content distribution happening once we can do just-in-time transcoding to scale. This concludes our presentation, and we are open to answering any questions that you might have.
That was great. Yeah, I really appreciate that. It's just you mentioned scalability at the end there, and that's definitely a question that the streaming media readers always have, is about any solutions, does it scale? So can you talk about any particular testing you've done, at scale?
Yeah, actually what we have done is we have done better than that. Actually, we have built a performance modeling tool. What it does, right, it allows you to build a traffic generator that kind of blasts into just-in-time transcoding system traffic with various models. And usually people use Erlang models of traffic generation or uniform models of traffic generation. And we have a traffic generator tool that generates traffic. What that means is it's going to make a bunch, as if there is thousands of users, it's going to make segment requests into Blazar. And then we have a performance analyzer that's trying to understand how the resources are being utilized. And it turns out that we have done a bunch of uniform requests as well as Erlang model requests. For example, what I show on the graph on the left is a 40 requests per second into a single GPU system. The goal is to get the whole idea is how many streams can I process on a given node that will allow me to saturate the utilization of all the available hardware resources. And usually we tend to be encoder limited in all of these systems. The encoder is the bottleneck. And so as you can see in this case, we are transcoding all the 40 requests under 200 milliseconds. Occasionally there is a burst up at startup or something like that to 300 milliseconds, but most of the streams get decoded in under 200 milliseconds. And the utilization of the encoder, as you can see, is creeping up to close to 100, 75-80% utilization. The decoders are well underutilized, which is what you expect in these systems, the pipelines in the GPU system. What I will mention is when people start seeing scale-up performance like this, one can imagine re-architecting GPUs as well as ASICs to take further advantage of scale-up parameters like this. So what ends up happening is one can imagine that the pipeline, one realizes that you have more resources on the decoding side than necessary for these applications. So you can imagine that those things can get scaled back power and be more power efficient. what we have seen is overall, we have done scale-up tests to thousands of streams and thousands of requests per second. And what all it requires is an on-demand spin-up of the number of transcoders needed, and we can scale up fairly linearly to fairly large volumes. And in fact, some of these are in field trials today with specific customers who are testing them to scale.
Yeah, and I imagine as the efficiency of underlying hardware continues to improve, Blazar will be able to leverage that. Is that right?
Absolutely. So this is a direct. So these are all. There is a direct scale up, right? I mean, the core capability of Blazar is actually the scheduling layer. So as hardware improvements happen, as ASICs or GPUs improve in performance, we will be able to appropriately leverage the available hardware and scale up the performance of Blazar. It's a direct proportion, indirect linear proportion, linearly scale up the performance as the performance of the GPUs and ASICs improve.
Okay, great. And thanks so much, Kumar and Jeff. This has been great. And check out the links in the chat, the contact links to the white paper and so forth.